thanks for the invitation. We are very happy to be here. So I'm Joseph Mikael. I'm heading the quantum effort at EDF. Oh yeah, it was. And I'm going to present you a work that some of my colleagues have done together with Atos, Eviden, Pasqal, and Institut d'Optique. Hopefully one of the authors of the paper is here, of the work is here, so his entrance, he managed to come. So yeah, we'll talk about material science, material simulation, and I try to explain why it is important for a company like EDF, and then Sergi from Pasqal will introduce you a brand new method, which is called slave spin methods to solve the kind of U-bar model with analog-based quantum computers. To us, material science is important to try to understand how material behave with time, how nuclear power plants behave, how steel age when submitted to radiation, to high temperatures. On the renewable energy, we have to understand how PV pans age with time to try to understand what's the level of investment that we are required to price our investment. And it's the same story for storage batteries, which are of a very different nature than the battery of electrical vehicles. To do so, usually what we are doing is to what we call a multi-scale modeling. So the smaller the zones that the zones they consider, the shorter the time that you manage to simulate. So if you simulate some very small zone at the atomic level, you won't be able to simulate your material for the next 30 years. So if you want to simulate some materials for the next 4 decades, you have to rely on finite elements method. So how does it work internally? We try to figure out whether a crack can happen in a material with some ab initio methods. And once a crack appears in our simulation, we want to assess whether the crack, how the crack behaves with time, with some finite elements methods. Okay? And I'll focus in this talk on ab initio methods. So we rely on DFTs that some of you may know, which is a great method with great achievements these last 2 decades, but there are still some limitations in the hypothesis that we are doing. So we need to go one step further. And we actually know what are the quantity of interest that we want to compute. We have some kind of observables that we have to compute on a quantum computer. Okay, so on the classical side, I guess we are at the state of the art of what we can do. So we want to rely now to try and see what quantum computer can bring. Yep. And I give the mic, the remote to Sergi.
Yeah, okay, so in the context of this interest that EDF has to study real materials with quantum simulators, we'll present now a case study that we've been developing at Pasqal as a joint effort with EDF also to basically solve the Hubbard model, so strongly correlated electrons with qubits. So let me first remind you the general loop that we have in mind when we talk about analog quantum simulation. So the ultimate goal is to study a real material. And for that, we need different steps. So first of all, of course, we need to get to a simplified model that we can treat. So that depends on a few microscopic parameters. But even these very simplified models are sometimes not easy to solve with a classical computer. And here is where the quantum simulator enters into play. In this case, you have here the one that we have at Pasqal. And this allows us to basically solve the model, so we extract the relevant physical quantities that we need. And then, of course, as a last step, we need to make a consistency check to make sure that the model describes the material, or otherwise, we might need to rethink a bit the model. So this is the general idea. Then for this project, we focus on a challenging problem, which is to study the two-dimensional Fermi-Haber model. So this is somehow the most simple model to describe interacting electrons. Basically, we just consider a term that takes into account the kinetic energy so that the electrons can hop from one lattice side to the other, and also a minimal interaction, so an on-site repulsive U. And even though this might seem a very simple model, it's actually the starting point to model very complex physical problems like high temperature superconductors. So this model can reproduce to a certain extent the phase diagram of these systems, also moire materials. But the challenge that we face in this project is that we want to simulate this model, which is based off electrons, so fermions, with a quantum hardware that is made of qubits. Okay, and this is fundamentally challenging because fermions, so collections of fermions and collections of qubits, have very different many-body statistics. So as you may know, if I exchange like two identical fermions, even though they might be very far apart, I will get a minus sign in the wave function. And this is very non-local property, while qubits are much simpler in this sense. So then we need to think of some strategy to tackle this. And in this project, we approach this within the slave spin method that has been recently developed. So it's basically a reformulation of the original problem, which involves interacting electrons, to a new picture in which we mathematically transform each of the original electrons into a new electron, actually. So we still have to work with electrons. But we introduce what's called a slave spin or a slave qubit that enlarges a bit the Hilbert space. So apparently, it makes the problem even more difficult. But through the slave spin mapping plus a mean field approximation, what we get is to this modified picture. So we now get two different problems to solve. One that involves free electrons. So we still have electrons, but they do not interact. So we can solve them very easily. And then the numerical complexity is mapped to a quantum missing model. So a model that is still difficult to treat classically, but at least is made of qubits. So we can simulate it. And two remarks for this picture is that there is a mean field approximation involved in the process, but it turns out to be a very valid approximation in very relevant systems, as explained in more detail in this reference, like ferro-based superconductors. And another subtlety that is important is that it's not that we have two independent problems. So as you can see here, the parameters of each problem depend on the solution of the other problem. Okay, this means that as pictured in this double arrow, we need to solve the two models in a self-consistent way in order to arrive to a final solution of the original 2D Fermi-Haber model. Then what we have to do in practice is to introduce an hybrid quantum classical solver. And this is what has been introduced recently in this very nice paper that is on arXiv by Antoine Michel, that is here in the audience, also Christophe. Basically, it requires two steps. One is to solve the free electron problem. This we can do in a laptop, even in a smartphone. So it's a very simple problem because these electrons do not interact. But then we need to still solve a quantum problem, a many-body quantum problem, which is the quantum missing model. And for this, with classical methods, we can just do it for very small system sizes. But the good news is that this is the model that is realized naturally in our quantum processing units. So basically, you can see here the two Hamiltonians map very well one to the other, and this means that we can use the simulator to analog simulate the problem of interest. And moreover, so the good thing with the quantum simulator is that we have a high degree of control over the interactions and the magnetic field in the Ising model, so we can really tune very well the parameters of the model and study it in a very controlled environment. Therefore, just very fast. So this is the picture that I showed you at the beginning. So now it's almost the same, but we get this modified step where we need to interface an hybrid and quantum solver in the quantum simulation part. Just to illustrate very fast, like two examples of what can we then do with this slave spin method. One is to study equilibrium physics. So for this two-dimensional Fermi-Haber model, the qualitative behavior is known. So at u equals 0, basically, you don't have interaction, so the electrons are free to move and are well described by quasi-particles. And on the other regime, when interactions are very large, at half filling, the electrons cannot move, so basically you have a Mott insulator. With the slave spin method, so these are classical results still, but still it shows that you can compute relevant quantities of the original model. So here we show how this quasi-particle nature of the particles evolve when we increase interaction. So basically here you have the metal to Mott transition. that we're going to study in a quantitative way. And this agrees qualitatively what is known with other numerical methods. The good thing that with the quantum simulator, we'll be able to go to almost the thermodynamic limit and study this transition properly. Another example that is even more challenging to simulate classically is to study quench dynamics. So we study a situation in which we start in the metallic phase, so the electrons are free, and we turn on high interactions very abruptly. So in a very small amount of time, we put a large interaction, and then we let the system evolve, and we're interested in studying how things evolve in this scenario. In this case, the prediction from the slave spin method is that the quasi-particle weight, so the nature of quasi-particles in the system, will exhibit this characteristic collapse and revivals. And this is very nice because it's some property of the 2D Fermi-Haber model that is known qualitatively again, but here we can do it in a more quantitative way. And these 2D dynamics are very challenging really to simulate with classical computers because you don't have like state-of-the-art methods are typically more suited for ground state physics or equilibrium. And this is, we believe, one of the most challenging situations to simulate classically. Still, the quantum simulator will allow us to go to almost the thermodynamic limit and study this nice physics. Okay, and with this, I conclude the presentation. So just let me very briefly introduce you our quantum simulation team at Pasqal, where we are working on the implementation of this slave spin method in our machines and also similar problems relevant for material science. And so we have different expertise in numerical methods, and also, of course, we work very close to experiment. And also, let me kindly invite you to our webinar next week, where the roadmap of the company will be presented. So if you're interested, feel free to join. And with this, I pass the word to Joseph, that will make a final remarks.
I wanted to take a photo of the QR code, actually, but... okay, so as a conclusion, so at EDF, as I told you, we are interested in this multi-scale modeling on this project. We focused on the ab initio part of the picture. We think we have some intuition that with this kind of methodology, by doing some improvements, we can go one step further. We could, at the end of the day, have something that we can't simulate classically. More going, so stay tuned on that method. I hope that we will issue some nice results by the next coming months. Thank you. So if you have any question, Christophe and Antoine, who are in the room, can ask. So thanks to them for coming.
Yeah.
No,
I think you can pass.
I will, yep.
Time for question. Who has a question?
Yep.
Yes. Marcin Dukowski from Aramco. So I'm trying to understand how the Fermi-Hubbard model help with the cracks and the simulations in the infrastructure, or is that?
Actually, it's the first step to try figuring out if we manage to do something with the Fermi-Hubbard model.
Okay. So
between this step and the crack in power plants, there's
still at least
some
one
months
in
will
between.
happen. Yeah.
Okay. All right. Thank you.
You want to add something, maybe?
The slave spin method is quite fine because you can add like a multi-orbital model, and you can study Fermi-Hubbard model with doping, things like this. So step by step, you can increase the complexity of your model towards the material of interest for EDF.